Good day, friends. Right now, let's try to solve 3 problems on torque in stationary state. So the first problem goes like this. A thin uniform rod rests against a smooth corner and it is held in equilibrium by a rope. The mass of the rod is 2 kilograms. The angle between the rope and the rod and between the rope and the vertical wall are alpha 60 degrees. Find the tension in the rope and the forces with which the rod acts on the floor and the wall. Okay, so first of all, what we need to find, it's tension force. And these two normal forces, the reaction forces, this one and this one, let's call this N floor, let's call this N wall. And we need to find these two things as well, NF, NW. Okay, so this is the image of our situation, and we have this kind of object which is just a certain degree above the ground, and we have this kind of rope which holds this bar. Yeah, this might be wood, this might be a metal bar, does not matter, any object, and it is held by the rope. Yeah. And we definitely know that these 3 angles are alpha. That's why it will be much easier for us to work with, because all angles are the same. Okay, first of all, where should we start? First of all, as this is the problem about torque, and torque is about rotational forces, right now let's try to write down the forces that we have in this situation. Definitely from the center of mass, we have mg. This is the weight. Also from this side, we've got this tension force. Yeah, this one, this tension, and nothing else. Yeah. So we, as any problem about torque, we can put pivot at any point we want, and I would suggest first of all to put pivot right here. Why? Because it cancels out 2 normal forces. As we know the formula of the torque, yeah, sum of torques equals to 0 in our situation because it's not being rotated, it is stationary state. But in general, it has a formula which is torque equals I multiplied E. Yeah, this I is moment of inertia and E is angular acceleration. The same thing as F equals ma. But this is for linear motion, this is for rotational motion. Right now we've got no any motion because there is no angular acceleration. It is not being rotated. That's why we know that the sum of torques, the sum of rotational forces are 0. But different kind of forces are trying to rotate different sides. Yeah, if we look at the situation, we definitely know that. Let's give some names to each one of them. Let's call this N floor, I don't know, this one should be torque 1. This thing is torque 2. Yeah, this is torque 3, and this is torque 4. Torque 4. Yeah. If you ask me why did I draw torques in that direction, well, I would say that it tries to rotate the same side where this force is directed. So torque looks at the same direction as force does. Yeah. Okay. And we know the formula of torque, which is Fr. Yeah. This is torque equals force multiplied R. Yeah. And we know that the torque number 1, as you can see, yeah, this one, torque number 1, and what's torque number 3, both of them are trying to rotate this thing clockwise. Torque number 4, torque number 2 are trying to rotate this thing counterclockwise, which means that, yep, let me write it somewhere here, torque number 1 plus torque number 3, because 3 is trying to help torque 1, but torque 2 is trying to work against torque 1 and torque 3. The same thing goes for torque 4, and it goes 0. And we can move both torque 2 and torque 4 the opposite side. It's going to be torque 1 plus torque 3 equals torque 2 plus torque 4. Yeah. And if we open this up, yeah, we don't have to open up torque number 1, torque number 2. Why? The question is why. The answer to it would be what? As we know that this is the force, yeah, this is the formula, and this is the force which is trying to rotate the object. And this is the distance of this force from the pivot. And if we look at these two, torque 1, the force which is trying to rotate is this thing, normal force of the floor. For torque 2, it is normal force of the wall. And as you see, both of them have this R 0 because they are 0 distance away from that pivot, okay? So what it means that torque 1 and torque 2 can be cancelled out. It's going to be torque 3 and torque 4 only. And right now, torque 3 and torque 4 will not cancel out because they have some distance. We don't know what this distance is. Yeah, this kind of distance. For torque 3, it is this distance. We don't know this distance, but we can give some meaning to it. Let's call this entire length of this block or object just L. It means that for torque 3, it is the half of the L. If you have a question why, I would say that the center of mass is exactly at the center. Yeah, this thing is equal length from both sides from the center of mass. That's why it would be just L divided by 2. Okay, good. So the force which is trying to rotate for torque 3 is mg, but not just mg itself, but its perpendicular component. Okay, so if we just imagine this, our rod or our object, let's say, lying horizontally, yeah, it looks like this, something, yeah, this kind of thing. From this perspective, our mg looks, for example, our pivot is here. Here we have the floor, and here we have the wall. Yeah, this thing is alpha. This is 90 minus alpha. We definitely know that. This is 90 degrees right here. And from this perspective, mg looks somewhere here. Yeah, if in this perspective, mg looks straight down, definitely when we rotate this rod, our mg also is gonna change its direction, something like this. Yeah, this is gonna be mg. Tension force has the same case. Tension force looks somewhere here. Yep, this is a tension. Okay, so, and we need only perpendicular components, which are these ones. Yeah, this has two components, this one and this one, but we don't need this horizontal component because it cannot rotate. It is not for torque. The same thing goes for this one. Tension force can rotate here, has a component here, and has a component right here. But this one cannot rotate, only the vertical component, which is perpendicular to it, because we know that it is not just F multiplied R, this is F cross product R. Yeah, this is my mistake. Yeah, F cross product R. And to find out what these things are, yeah, let me continue this line somewhere here. This is 90 degrees. This is going to be alpha. And if this is alpha, it means that this thing, this line, is going to be mg sine alpha. Why sine? Because as we said before, we have two components, this one and this one. However, we can draw that vertical component right here. That's not a problem. And if we look at this component, it is opposite to angle, and it is parallel to this one. It means that both of them are the same. So this is mg cosine alpha, mg sine alpha. I'm sorry. The same thing goes right here. If we just continue this line somewhere, yeah, let me choose violet, like this. Yeah, this is 90 degrees. Then this thing is going to be 90 minus alpha. No, the angle, which is given right here, is alpha. Yeah, this is given alpha. Yeah, this is already given. This is already given. Yeah, let me just turn it. Yeah, that's not 90 degrees because it was already given to us. Yeah, I'm sorry, that's my mistake. This was given as an alpha, and if this is alpha, the same thing goes right here. It's opposite. This one is sine, and it is just parallel to that one. So basically, we just say this is tension sine alpha. Okay, good. We've got our components which are trying to rotate. It's not just tension. It's not just mg. It is the components which are perpendicular to the object which we are trying to rotate. Okay, tension 3. It's for mg, but we know that it's perpendicular component. It is mg sine alpha, and the distance, the r in this case, is L divided by 2 because it's that distance away from the pivot. Equals, for torque 4, it is tension sine alpha, as we said before, and it is the entire distance from the pivot because it's the other end and tension force is the other end. Okay, yeah, so this thing's going to be L. As you see, this is really convenient to us because L's are going to cancel out, sine alpha is going to cancel out, and we exactly know what is the answer for tension force. It is mg divided by 2. Can it be our answer? Yes, it can, because our mass is given to be 2 kilograms, gravity is just 10, let's say, this is 2, and if we just cancel those out, our tension force will be just 10 newtons. Okay, good. What about normal forces? Yeah, we have found this thing. This thing is already successful. What about normal force and both normal forces by floor and the wall? Okay, well, in this case, we don't need much torque. We just can work with just a simple Newton's second law. Yeah. Let me take this a little bit far so it didn't distract us. Yeah. It's still there, but just for this case, yeah. Let's get rid of this. Okay. What I'm trying to do is next thing. As this thing has a torque of 0, we need to mention that it has also the force. The sum of forces equals 0. Why? Because this thing is not moving in linear state. It is the sum of forces equals to 0, which means that in sum of forces in horizontal axis equals to 0, sum of forces in vertical components equals to 0. Okay, so horizontally, what do we have? Horizontally, we have this normal force wall, but the problem is about this tension. It has two components, and let me break those two down. One is like this, another one is like this. Yeah, okay, as you can see, this thing is exactly cuts it in the half. If you say like why, I would say this thing is 90 degrees. This is that the half of this alpha, yeah, because we know that this is 60 degrees. This alpha, we know that 3 alphas is going to be 180 degrees, and alpha is going to be just 60 degrees. If this is 60, this is 90, this is definitely 30, which means it's just a half. It's perfectly cut in the half. Okay, so but right now, let's call it just alpha divided by 2. Yeah, yeah, good. If this is alpha divided by 2, this small angle, let me put it here somewhere. It means, well, basically this angle is also just alpha divided by 2. This thing, alpha divided by 2. And this one is just what? This thing is tensions cosine alpha divided by 2 component, and this one tensions sine alphas alpha divided by 2 component. Okay, right now we can work with it easily because it's much easier to work with. Everything is in the same direction, just vertical, horizontal, yeah. Horizontally, we've got what? Normal of the wall just equals to tension force of cosine alpha divided by 2, yeah. We've got this formula. Yep, sum of forces equals ma, the Newton's second law. But our a is 0, that's why this is just this formula. Okay, then it would be what? It means that normal force of wall is trying to push right, tension force of cosine alpha divided by 2 is trying to move left, but none of them is winning. That's why it means that they're equal. But so you didn't get distracted, I would write it like this: normal force of the wall minus tension of cosine alpha divided by 2 equals 0. So basically this thing, yeah, sum of forces. And these two are opposite, that's why it's just minus. Okay, and if I move just t cosine alpha there, it's got to be just normal force wall equals t cosine alpha divided by 2. And can it be our answer? Yes, it can. Why? Because we have found our tension, and it's got to be just mg divided by 2, if I'm not mistaken. Yeah, and this is just cosine alpha divided by 2. And can it be our answer? Yes, it can, because we are given of mass and the angle. G is constant in our case, actually, and 2 is just number. So let's calculate it. It's got to be 2, this is tan, 2, cosine, we have proved it is just 60 degrees, divided by 2, it's got to be, yeah, this thing cancels out, this is 10, cosine 30 is going to be 1 divided by 2, right? No, it's not right, it's square root of 3 divided by 2, yeah, this is this one. And right now, it means that this is just 5 multiplied square root of 3. It's, if I'm not mistaken, 5 multiplied 173, which gives us something about 865 newtons. Yeah, pretty good. This is our answer. Yeah, let me just highlight these answers. Oops. Yeah, let me highlight these answers so we can see them at the end. Our answer is this one and this one. Okay, good. And the last one is about normal force of the floor. So what we can see is that normal force of the floor and tension sine alpha divided by 2 are trying to move it upward, but mg works against them, and it totally does its work because none of them can move in their direction, which means that just the same thing. I write it somewhere here. Yep. Let's say normal force of the floor plus tension sine alpha divided by 2, because they are trying to help each other, but mg is trying to distract them, and this is going to be 0. If I just want to find normal force of the floor, it's going to be just mg plus there that side, yeah, if I move it there, and this is minus sine alpha divided by 2, yep. And we know that tension force is mg divided by 2, and floor is going to be mg minus mg divided by 2 sine alpha divided by 2, yep. And we can see that mg is a common factor, that's why just and floor is going to be just mg. This is going to be 1 minus 1 divided by 2 sine alpha divided by 2. Can it be our answer? Yes, it can, because we have mass, gravity is just a constant in our case, and alpha is given. Yep, pretty good. And let's just put in numbers. Normal force of the floor is going to be just 2 multiplied 10. This is going to be 1 minus 1 divided by 2 multiplied sine 60 divided by 2, which means sine 30, and it is 1 divided by 2 as well. Yeah, let me do it. Yeah, this is going to be just 20. Let me just say it's 20. This is 1 minus 1 divided by 2, and sine 30 is 1 divided by 2 as well. This is going to be 20, 1 minus 1 divided by 4, and it's going to be 20. Okay, this is going to be 3 divided by 4, yeah, and we can cancel these out. This is going to be just 5, and our answer would be 15 newtons. Yeah, this is our answer for this case, and this is our physical answer. Yeah, this one. So basically, yeah, pretty good. I like it. I hope that you understood everything well. Yeah, but if you have any questions, you can write me privately. We're going to solve problem number 2 next video. And thanks for your attention. Bye.